Okay, so thank you, Spring, for the kind introduction, and thank you also for the organizers for having me. And yeah, I'm very happy to share some of recent findings which we could achieve in this field of traffic. And I would like, since I'm an applied mathematician, I would like to maybe give you a glimpse of a couple of things which I think where maybe mathematics can somehow contribute to this topic of social dynamics beyond vehicular autonomy. And so for that, I was thinking about three things essentially. So I would like to not go into depth in all of those, but want to give you at least a glimpse of the mathematical concepts which possibly could be used for somehow dealing with novel problems which arise when you now not only consider autonomous cars, but also interaction maybe with bikes or with pedestrians and so on. And so one thing I want to talk about is how you can maybe from a mathematical point of view to model now more heterogeneous conditions in traffic, like, as I said, like sudden pedestrian crossings, for example, on a road, or like somehow shared lanes between bikes, cars, and so on. So how can this somehow come into classical traffic flow modeling? And then second, I want to talk about something which might also be present in certain environments here, where you have maybe cars and you have pedestrians, and so you have typically different sizes of groups, typical different speeds, so you have different scales to consider. And so maybe there's an interesting mathematical question on how to deal with these different scales in a somehow in a well-posed way, or in a way that you get consistent, for example, control actions or something like this. And last, maybe I want to talk a little bit about control. And so if you now consider maybe the highest level of autonomy, these level 5 autonomous cars, they have a certain control mechanism in order to determine their speed. And obviously you want also to be sure that this is stable, robust, or something like this. So there's also, I would say, some mathematical questions behind. So this is what I want to do, though I don't want to somehow give you all these mathematical details, but maybe highlight where I would see mathematics as a possible tool to answer or to describe some of these effects. And more precisely, so I have now on the left here again, these three aspects I just mentioned, I've ordered them in a different way. And on the right, I will tell you what I want to do in the next, in this talk, namely for the first aspect, so on this heterogeneous traffic, which will also be the first part of this talk, I would like to show you what we did with uncertainty quantification methods. So I would like to somehow describe, we can talk about this if this is valid or not, but I want to describe this heterogeneity by an uncertain parameter or by some stochasticity which enters classical models. And then I want to show you what can go wrong and what kind of maybe new mathematical questions arise here. And this I will do on the fluid level description of traffic, of vehicular traffic. And then I want to say something on these different scales. And this I want to do in the context of control, because first of all, on the classical modeling context, there's already plenty of results. And so I want to show you how these results can maybe be translated towards a control setting. And last, then I want to say something about stability and optimality of control settings and how this can be done also in a consistent way. And as I said, and here I will, in the control part, I will then focus on maybe model predictive control. And for the other, we will talk a little bit also on swarming models, which could be used, for example, to describe pedestrian flows. And so my aim is, as I said, to give you these three somehow pieces and show you a little bit on the mathematical details. Of course, if you have questions or further comments, I'm happy to answer and to also point to some of these papers which we have in this. Yeah. So I would say I start with, I start with maybe the mathematical aspects which I found interesting in this heterogeneous traffic or in the modeling of heterogeneous traffic conditions. And For that, I would like to show you this first slide where you have the different scales of modeling traffic, vehicular traffic, which I would see in the moment. So I don't want to discuss all these kind of equations, but I want to introduce these scales because this heterogeneity can, of course, appear at every scale. So on the left, at least on my left, you have what is called a macroscopic scale. So this is a scale where you describe pedestrian or vehicular traffic motions by really describing individual trajectories of cars or pedestrians or whatever you want to model in this traffic environment. And so there are several models available, which I don't want to go into detail, but there are simple models which just do velocity relaxation, and there are more prominent models like, for example, the follow the leader model for vehicular traffic flow, where you have somehow an anticipation term of the driver's velocity of the car in front of you. And clearly on those levels, you can already have heterogeneity of already control aspects, which I want to come to later. And then you have a middle level, which would describe, which is a mesoscopic scale or a kinetic scale. And there will be a couple of talks also in this workshop on this scale. And there you have essentially an aggregate description of these individual cars. So you say that you look for the probability to find a car at a certain point in space and velocity, and at a certain time, and corresponding to these microscopic models on the left, you have in the middle corresponding kinetic models. And there is sometimes rigorous, sometimes formal. There are results which relate somehow these models, where you have convergence, for example, in the case of many cars. And you have different ones, and you can already do a little bit of analysis. This is done here in red, but I don't want to enter this now on this level for these cars. And finally, you have what is called a fluid or a macroscopic scale, which describes now not a distribution, a probability distribution of cars at a certain point, but which describes rather car density and car velocity, for example. And one of the famous models is this Lytle-Witham-Richard model, which is somehow a limit for epsilon to 0 of this bottom right model here, of this Oraske-Zhang model, which is somehow the first extension of this WR model. And there are other models on this side. So you have these three scales, and you have relations between those. For them, you can go rigorously from one scale to the other. Some are formal computations and so on. And so in the beginning, I had that if we want to describe something, clearly we have to decide on which scale we want to do that. But one point of this talk will be that maybe it's also interesting to look at the effect of, if you control on this scale, can the control somehow be transferred to controls or from microscopic essentially to macroscopic scales? And what kind of properties can you gain or can you lose? And if you have this, if you can go through this diagram also for other aspects, for uncertainty, for control, and so on, for stability of controls, then maybe you have somehow a consistent hierarchy which allows you to deal with many cars, which does not have any dimensional dependence in this sense, and so on. So therefore, I wanted to show you this slide. Now, for the first part, where I want to talk a little bit on uncertainty, there are a lot of results on this, what is called the ODE level, where you have just ordinary differential equations which describe your model. There's also a lot of work done on kinetic level, and I want to show you now what can be done maybe on this last level. So the macroscopic level, which would be more like a broad view on vehicular flow, where it's really reasonable. You have enough cars to talk about density of cars or average velocity of cars. And so if you now think of one model, just to exemplify this discussion, I took here what is called the Oraske model. So you have a model which describes on this, as I said, on this last level, on this macroscopic level, the evolution of the density of cars and of their velocity, and maybe of an additional property, which is called Z here. Then you have a nonlinear hyperbolic transport equation plus maybe a source term, which gives you possibly a relaxation to some desired equilibrium velocity. I don't want to discuss the properties of the models. There are a lot of other talks on this kind of model, even in this workshop, so don't want to say much about that, but it's a nonlinear hyperbolic model because of this transport. It's simple because it's only spatially one-dimensional, but still has some interesting features. And now what I want to say is, or what I want to do is, okay, there are a couple of parameters. First of all, there are initial conditions. For example, there are boundary conditions, and there is also here what is called the relaxation time. So this is a time which somehow controls how quickly you reach your desired velocity. And you can say that because of maybe heterogeneous conditions, either initial boundary or even this relaxation type or even the equilibrium velocity is somehow unknown or somehow undergoes random perturbations. And so what you want to actually solve is not this kind of deterministic model, but maybe it would be better to solve somehow a random PDE, where the randomness could be in, as I said, in either of these conditions. An example is given here where I just say that, okay, maybe the relaxation time is different. And now, of course, it's now the good question how to model this randomness. And I don't want to enter this discussion here. I would say that we can model the randomness in the way that I would say that it's what is called a parametric uncertainty. So this random variable psi, which has a given distribution, which might come out of data or which might be empirical, would now enter this equation in the sense either here, for example, in this parameter or in the initial or boundary condition. And this would lead essentially to an equation which is now not only posed in time space, but also in the in this parameter psi, which has a given distribution. And so all these functions now, rho, v, and z, and I only write this for rho now, but it's the same for v and z, would now depend also on this random parameter psi with a given distribution. And now you might be interested to ask, okay, what is now the expectation of rho with respect to psi, and what is the variance? And can I now make maybe predictions of future traffic given a certain distribution of my typical relaxation times, or given a certain distribution of initial conditions, or given certain fluctuations of boundary conditions. And so this is, of course, this topic of uncertainty quantification for these nonlinear hyperbolic equations. And so this is again the same equation. Now I did write the tau of psi here explicitly, and now the question is how you solve this. And there are clearly a lot of methods around. The simplest would be that you just sample in psi and do like a Monte Carlo or maybe multi-level Monte Carlo version integration, and then you get your expectation and your variance. Or you do stochastic collocation, so you discretize, or you do a moment method. All these methods are what is called direct methods, so you just need to solve this plenty of times, and you get maybe statistics for the expectation and the variance, but maybe sometimes you need also further information, so you need maybe the distribution of this variable even in psi space. And then a possibility would be generalized polynomial chaos expansion, which is essentially a truncated series expansion of the solution rho in terms of the variable psi by coefficients, which I call rho I of t of x, and by suitable base functions, phi I of psi, which you would choose according to the weight or the weight at which you would choose according to the distribution of this function psi. So for example, if it's a uniform distribution, you would maybe take orthogonal functions, which would be then Legendre polynomials. And so what you do is formally you expand this rho to an infinite series in terms of these coefficients, and then you truncate, and you do, of course, the same for v and z. And then you get equations for these coefficients. And the expectation, for example, for the Legendre polynomials would then be the equation for the first coefficients. Of course, due to the nonlinearity here, those equations will be coupled. And this is not the only problem, but this generates now a mathematical question. What about the properties of the system which these coefficients fulfill? And so here is a formal, here's a formal system. So I have put in the series expansion. I have tested in a Galerkian projections against some test function, against the functions phi. And so on the left, I get an evolution equation for the coefficients, and here I get the flux. For if I only expand to a single mode, then I get again the deterministic or Raster model in this case. If I have a finite truncation, then this formulation says essentially that you project your infinite dimensional functioning psi to a subspace of these 2k plus 1 polynomials. And the, no, it's actually k plus 1, sorry, polynomials in psi. And then the question is, what do you do about this term? Because you don't want to leave this term like that, it's not closed. And so this means that you need to close, essentially, that you need to project this nonlinear function f towards this polynomial space. And this could be that you just need to project this product. For example, if you would project this, you need to compute this tensor of these three polynomials, which you can do a priori. If you do that, if you proceed like this, then what you realize, if you expand O, V, and Z, you realize that the resulting system, which I've not written, but this loses hyperbolicity. So it loses a property which the original model had. And now you can say maybe it's not relevant, but what you can see here is this is a reference solution to a problem where the initial data was uncertain, and the reference solution is computed with a high order Monte Carlo integration. And then I did compute the same thing with this projection, just as I explained to you. I get a non-hyperbolic system, but I have a numerical scheme which could anyway solve that. But you can see nicely that this solution which you get here in red has enough, so you cannot see much difference between red and blue. Blue is the mean, red is the mean plus and minus the variance. Therefore, these are three curves, but this is not the main point. The main point is that you get a qualitatively wrong solution. So you have an expansion for a system which, due to the loss of hyperbolicity, you don't recover the correct somehow solution. And so this makes it an interesting mathematical problem. And of course, for that particular problem, there's also a solution. The idea is that you don't expand in all three of these variables which appear, you only expand rho and z, and recompute v according to this formulation, which is particular to this Oraske model. And you need then to project this system. And this amounts, of course, to solve, if you do these computations, to solve a linear system for the coefficients of v, once you know the coefficients of rho and z every step. And this p of rho needs to have a certain property. So this is a matrix M, which you had seen before, this triple product. Don't think the details are so important at this point, but this formulation, if you do it in this, and if you project precisely using this formula, then we can prove that the resulting system is in fact stays hyperbolic. And numerically, what you see if you then solve this formulation, you see that you recover the qualitative correct solution. So this is the same example. Reference solution is also the same picture. And you have again in blue the mean, and in red and blue, the mean, and in red you have a mean plus and minus the variance. So, and of course, this is now just for one of these single equations on this fluid level. We have discussed this somehow, these properties, how to, in some sense, how to define suitable projections, how to define suitable variables in which we do the series expansion in order to get correct solutions. And so there is, I would say, interesting mathematical things once you include this uncertainty. We have also some more results. We can prove that this, in fact, that this linear system has always a solution. by proving that this is really positive, this P of rho is really positive definite. I already told you that this system which we then get is actually strictly hyperbolic, except in the vacuum. And remember, initially we had a source term on the right-hand side, which does not play any role for this hyperbolicity problem, but this source term controls if the model is far away from somehow a simpler LWR model. And so we have also kind of consistency, so that for if the rho is deterministic and if the uncertainty would be only in the initial data, then you converge to the LWR model. And finally, a further picture, you see that here, what you want, but what we haven't proven so far is, of course, I said in the beginning that, wrong direction, in the beginning that we have a truncated series, so you would like to converge for k to infinity to the true solution, and so you would like to show even this convergence. And at least numerically, what you can see is this is a picture for an expansion with only two modes, K0 and K1. And here's the reference solution in black in the middle, and then you have the mean in blue and the variance around that in red. To see that, okay, this is clearly far away, but if you go to K, this is 63, so it's 64 modes, then you almost captured the exact solution. So numerically, you observe this. And I should say that depending on where you do this, namely either on the fluid or on the kinetic level, you have already proofs of convergence for K to infinity, for example, on the kinetic level, but I'm not aware of some on this for this or Ruskell model. So I see also there's a question in the chat. So because of the discontinuities, you see that this is in fact this would be a discontinuous solution, but since I plot the expectation precisely as is written there, you see that it somehow smears out. Okay. So there are a couple of interesting things to discuss here when you insert uncertainty, I would say, on this fluid level. And clearly, probably similar points can be made also on the kinetic or on the microscopic level. But I don't want to go into further details. There are, I can give you a lot of references if you are interested. There are more results available. What I want to do next is I want to show you something, because in the end we want maybe to also control on different levels our dynamics. And so I want somehow a similar picture like that, which just links the models. Maybe I want a similar picture which also links the control problems. And in order to somehow exemplify this a little bit, I need to consider, of course, you see that there are various limits which you can take here from different sides. So I want to do maybe the microscopic to the kinetic one, this first link, which is here. And this is a link which you can typically establish when you take this number of particles which interact, so either the vehicles or the pedestrians or the swarming behavior, when you take this limit to infinity. And what you typically see is this is a model which we have also seen with Andrea Bertozzi yesterday. This is time, this is opinion formation, and you see that there is formation of certain opinions on the particle level, on the top side, on the top left, uncontrolled. This is somehow a fluid-like or kinetic approximation of this same picture, and you see that somehow just by looking at this from the eyeball, you see that there is a similarity, and on the right you have an additional control added, and you also see some similarity in these two pictures. And the question is, in which sense are these two control actions similar or not? And so what I want is I start maybe with a typical crowd motion problem, just for a position or for for property xi, which interacts with other xj's through some kernel p, and you have a control u, and this control should be chosen to minimize a certain cost functional, which is called phi, and there's some symmetry here because I interact with all other agents j in a similar way, so I have a sum here, and I have a sum also in the cost function. And so my question is, I already know what is the limit of this as a model, but what is the limit of this as a control problem? And this could be relevant if you want to have, for example, controls which are in some sense independent of the number of agents. And so our goal is to find this consistent control for any number of agents. And as I said, just for here, exemplify on a nonlinear swarming model. This is a picture of a linear model, but here I want to treat the nonlinear case. And in principle, what you can think of, you can do two problems. So you have one problem on the microscopic level, far left in my first picture. You have one problem on the mesoscopic level, the middle column of my picture. These are just formal limits of this cost functional. So you get on the mesoscopic level, you get this kinetic density, which describes somehow again the probability to find particles at certain time, at certain space. And corresponding to that dynamics, you would write dynamics which would look like this. So the dt mu plus the divergence of this operator g, and g clearly comes out of this function p. And I don't give you the details. You can write this explicitly, but I think for this presentation, this is not the point I want to make. So there is a link between these two dynamics. Now the question is there now also a link, say, on the optimality systems of these two? And the first thing, so for this problem P, this is of course a classical optimal control problem on ODEs. So there is what is called a Pontryagin maximum principle. You find an adjoint vector corresponding to this xi, and you get a coupled system of ODEs. And then, of course, you can say now that this coupled system of ODEs is now my new model. So let's derive for that model also a mean field description. This would give you a description which not only depends on the state and the time, but also additionally now on this new variable, the adjoint variable. On this level, on the other side, on the PDE level, for this problem, what would you do? This is optimal control with partial differential equations. There's constraints, so you would need to define a suitable scalar product, and I will come back to that later. A simple choice would be in L2, the scalar product. Then you would write the Lagrangian, you would differentiate, you would check all these properties. What you would end up with formally would be also, again, of course, the transport equation for mu, and then an equation, a second equation for the multiplier, which would now be, of course, a function depending on t and x, and this would solve somehow the linearized system to that, plus the cost. What you can maybe immediately see is, and clearly now in order to have now consistency between the mean field equation corresponding to the optimality system of this ODE and this L2 first order optimality system from the PDE level, you would now need to link this function g to mu and lambda. And okay, clearly you observe that here you have phi. In the Pontryagin, you would of course get gradient of phi because you would differentiate the cost. So maybe so you need to link this in a proper way, and you can do that. And the trick or the idea is that you can maybe decompose this function g of the ODE level by in another function mu, which would fulfill this equation in the end. And a conditional probability. So given x, this mu c would be a probability distribution in z. And then these two problems we can show are in fact equivalent. So you would get a consistent control provided that the gradient of the continuous multiplier is in fact the expectation of the conditional probability of this ODE system. And this is somehow a consistency condition which would link these two scales, which we had, the microscopic and the mesoscopic, now on the optimality. And you can use that first to interpret somehow your continuous problem. So you can say that, okay, the correct scalar product to choose here would be in fact the gradient of lambda. So it's a weighted space in which you should do that. Or you can use that in order to say, well, here on the microscopic level, I usually have a problem with the dimension. If there are many, many particles, clearly this problem gets more and more complicated. So I prefer to maybe solve this one. And how should I solve this one? Well, this mean field formulation would allow you also to design numerical schemes which have maybe a different order of complexity than the ones for the ODE. So depending on the number of particles you have, and given this condition, you can now go through this hierarchy also on the optimality level. And of course, you cannot only do that on this optimal control setup, but also in a game theoretic setup if you want, but I don't want to show this picture. So you can extend this picture to this picture on the models to a picture of the optimality systems, and this might be relevant in case you want to have controls which are consistent. What is certainly maybe not realistic here, if you think now of how to implement that in your preferred autonomous car, is that this is all optimal control. And typically, I would expect that you need to introduce a certain number of uncertainties, as I had in the first part of my talk, also in this control setting, because maybe you predict a certain time horizon in which you can now, or in a certain way, control your autonomous vehicle or control traffic lights or whatever, but then maybe some unexpected things happen, so you would like to somehow restart this control procedure. And clearly, probably most of you are familiar with this concept of model predictive control. So you have a car and this observes some unforeseen things and then has to decide if it's turns to 1 or 2 or 3. And it would do that in the following way. So we are sitting at time Tn, we observe our current state, which could be influenced by somehow external conditions. And then we would maybe give ourselves a prediction horizon, which is here called capital N. And we would maybe optimize over this prediction horizon. And then we would apply this control here on the same horizon or even on a shorter horizon. And at this point here, we would then somehow take new observations into account and repeat this procedure. So it's a classical control strategy. And if you do that for this particle model, which I had in the beginning, and you look at the performance depending on the horizon, what you can clearly see is, of course, if the horizon is very small, 2 time steps compared to 10 time steps, the action of the control, so here the control goal is, of course, to push all people to the center, or all particles to the center. The control action is, of course, not optimal. So clearly, it's probably obvious also from this concept that the longer the prediction horizon, the more efficient the control is. Now the question is, and this comes now to the last point, once we have designed somehow suitable controls, what can you say about stability, robustness, or performance? And okay, I cannot say, and I would like, in view of the middle part of my lecture, to say that also these concepts should be independent if I have 100 participants, 100 cars or 1 million cars. So if I'm on the microscopic, on the mesoscopic, or on the macroscopic level. So I want estimates which are in some sense independent of the number of particles. And I have, so far there is a result only on the optimality of the horizon in this regard. So what one can do is, even for general dynamics, with ODEs, you can look, of course, at the value function. So this is the future cost which you would have starting at the time tau, and at a certain state, capital Y, which would be the initial conditions, so which would be precisely here, so at this point where you are standing, and then you have the future costs up to the terminal time, which is this V star. And this you can compare with the value function of the model predictive control, so of the control which you generate by having a truncated prediction and simulation horizon. And the result which one can get for finitely many particles was proven by Grün in 2009 is the following, that under certain conditions which are not listed here, in particular on the growth of f and the function h, under certain conditions you find a number alpha between 0 and 1, so that the performance of your value of your model predictive control is only a factor away of the optimal performance. And clearly this factor alpha can be computed explicitly only for couple of examples, unfortunately, but there's still some research to do. But this factor alpha depends strongly, of course, on the prediction horizon. Clearly, if the prediction horizon is infinite, then this tends to 1, and you have the same value. And so what we tried to do is, this was a result, as I said, for general dynamics, but finitely many particles. And so what I wanted, or what we managed to do, is to extend this result to the case of infinitely many particles. So this essentially, this estimate, I think I have it on the, I don't have it on the next slide, but this estimate also holds if you have any number of particles. So this estimate is consistent across this hierarchy of models, at least across the two first parts of this hierarchy. And this constant, in particular this alpha, does not depend on the number of particles. This was what we could prove. So we could extend, as I said, this result to this mean field, to this mesoscopic level for infinitely many particles, and this number was independent. You could also compute and do some numerical tests, which would show you how far you are away given the model predictive control horizon. And you see that the alpha, of course, gets very bad if the model predictive horizon is small. But at least if you can, under certain conditions, compute this alpha explicitly, and then it allows you somehow to a priori decide how long this horizon should be in order to have a kind of optimality. So V star would be the best the open loop value, the value of the value function for the open loop control, and 1 over alpha is then somehow the factor with which this deteriorates. Though maybe performance is not the only issue. You probably care more about robustness, and so unfortunately I don't have a result on this, so clearly would also like to know how robust this MPC control is, independent of this number of particles, and maybe for a realistic model. But as I said, so I wanted to show you what kind of mathematical tools or mathematical problems you can arise in this interaction of somehow vehicular traffic with other traffic. And with this, I want to summarize and would like to say that, okay, there are a couple of things which I showed you, and I only gave you, of course, a couple of pieces on that. I wanted to say that maybe heterogeneous aspects can be modeled by these random variables, and this might lead to interesting mathematical questions, for example, for these fluid-like models. As I said, so on the kinetic, on this mesoscopic level, there have been already results, in particular for somehow flow, which is appearing in gas dynamics. And then I wanted to show you that if you're interested in control questions, for example, because you want to design something for these autonomous cars, then and you want to include aspects where it's relevant that you go also from microscopic to mesoscopic scale, then you can do that under certain conditions. And if you say that you want to do it more from a more practical point of view, even with this MPC, there are also maybe some interesting questions still open. And so part of this work, of course, has been done in collaboration with two students now of mine, Stefan Gerster and Lisa Tacomini. Other parts have been done with Christian Ringhofer and Mattia Zanella. And of course, I'm happy to point you to these references. So I think I'm almost out of time. So with this, let me thank you, and happy to take your questions or put my email, or if you want to contact me. Thanks a lot.